In this last section of the chapter, we want to look at some additional identities or some additional problems that we can work using identities, and also there's a list of some 8 special identities that we're not going to really bother to memorize here, but I want to show you how to use some of them. So first, let's start with this first problem I have written over here. Sort of a complicated looking expression. We want to simplify the cosine of inverse tangent 1/2 plus inverse sine 1/2. Now inverse tangent 1/2, that's an angle. Inverse sine 1/2, that's another angle. So I'm going to say that this has the form cosine of A plus B, where A is inverse tangent 1/2, which means that tangent A equals 1/2. And then B is inverse sine 1/2, which means that sine B equals 1/2. Now if I want, what I can do is, just for reference here, since I inverse tangent 1/2, when 1/2 is positive, I know I'm talking about an angle in the first quadrant. Same with inverse sine. The inverse sine of 1/2, which is a positive number, this is in the first quadrant. I'm just going to, for reference here, draw a couple of triangles, and I'm going to call this, in this triangle, angle A. It's a right triangle. Inverse tangent, or tangent of A, is 1/2. So I'll mark this side with 1, this side with 2, because tangent is opposite over adjacent. And then I know that my hypotenuse will be, by the Pythagorean theorem, square root of 2 squared plus 1 squared, square root of 4 plus 1, which is square root 5. Now over for this one, I'll draw the same kind of triangle. Remember, this is just for reference. I'll say this is angle B. The sine of angle B is 1/2. So the opposite side divided by the hypotenuse is 1/2. By the Pythagorean theorem, then, this side must be square root of 2 squared minus 1 squared, square root of 4 minus 1, or square root 3. So now I can go back to my original formula here and expand using my cosine A plus B formula. Cosine A, cosine B, minus sine A, sine B, my expansion formula for cosine of A plus B. Now I'll just go over here to what I've written down with my triangles. Cosine of angle A, adjacent side over the hypotenuse, 2 over square root 5. Cosine of angle B, adjacent side over the hypotenuse, square root 3 over 2, minus, that's that subtraction sign. Sine of A, opposite side over the hypotenuse, 1 over square root 5, times sine of B, for angle B, opposite side over the hypotenuse, 1/2. So I end up with 2 times square root 3 minus 1 times 1, which is 1, all divided by 2 times the square root of 5. Now if I want to, I can simplify this using a calculator. I could rationalize the denominator on it. There's a whole bunch of things I could do to change the form of this, but what I wanted to really just show you was that here is another form of my cosine of a sum formula, where my 2 angles are written in terms of my inverse tangent and inverse sine. So there's a lot of trigonometry involved in working this problem right here. First of all, I have to have this formula memorized. I have to know the definitions for inverse sine and inverse tangent so that I can write them as a tangent and sine expression. And then I'll use my little green rectangles here, or my little green triangles here for reference to find sine, cosine, or whatever I need for those 2 angles. Let's go now and look at our second problem. I have cosine of 2 inverse cosine x. Now remember, this is an angle, so I'm just going to call it angle A. That means that this is the formula, or I can rewrite this expression as cosine of 2A, where A is equal to inverse cosine of x, which means that the cosine of A is equal to x. Now if I want to, I can draw another one of my little triangles here like I did in the previous problem. Right triangle, call this angle A. The cosine of angle A is x. Cosine is the adjacent side divided by the hypotenuse. To get that to come out to be x, I'll make this x and this 1. That means that this side is square root of 1 minus x squared. Hypotenuse squared minus x squared. square root of that whole thing. But actually, in this case, I don't need my little triangle because the cosine of 2a, I have 3 different expressions I can use for that expansion formula. I'll use the one that just involves cosine. 2 cosine squared a minus 1. And I know that the cosine of a is x, so this is simply 2x squared minus 1. So here is the simplified version of this expression right here. And I think I've forgot to write down here that I have a restriction on this variable x, that x is greater than or equal to 0. So if x is a positive quantity, now I know I'm talking about an angle here in the first quadrant. So cosine of 2 times angle A, I choose this formula, 2 cosine squared a minus 1. I know if I'm letting a be equal to inverse cosine x, then the cosine of a must be x. So I just simply take this x for cosine a, substitute in this, 2x squared minus 1. So in this case, I didn't even need my little green reference triangle. Let's look at the next problem. Okay, I have 10 sine 5x cosine 3x. Now, to work this problem, and again, what I want to do is simplify, I have to realize that this looks like the formula that I have in the book, sine A cosine B, and you know by looking at the formulas in the book that this can be written as sine A plus B, okay, plus sine A minus B. So here I have sine of one angle, cosine of another angle. That's what this looks like, sine of A, cosine of B. My whole expression, though, is 10 times this, so what I'm going to do is multiply this expression by 10, which means that this expression here will be multiplied by 10 also. And let me see, I think I forgot one thing, and that is a coefficient of 1/2 on this whole thing. Okay, that's kind of messy, but I think if you look in the book, you'll be able to see that formula. So all I'm doing right now is writing down that formula that's in the book for the sine of A times the cosine of B. It comes out to be 1/2 sine A plus B plus sine A minus B. I simply noticed that the formula that I'm looking at is 10 times sine A cosine B, so I'm going to put a 10 coefficient here, a 10 here. All that means is that 10 times 1/2 is going to give me 5. Let's continue with this problem now. So this is going to come out to be 10 times 1/2, which is 5, times sine A plus B. Well, if A is 5x and B is 3x, then I'm going to have sine of 8x plus cosine of A minus B. Well, if A is 5x and B is 3x, 5x minus 3x is 2x. Whoops, so I want to write sine 2x. So this expression, what's good about this problem right here is this. Here I have a product of 2 trigonometric functions. Sometimes it's convenient to be able to write that product as a sum in some engineering fields and scientific fields. If you have a product of a sine and a cosine, 2 trigonometric functions like this, what you'd like to be able to do is write them as the sum of 2 trig functions. So if that's the case, I can use this formula, sine A cosine B is 1/2 the quantity sine A plus B plus sine A minus B. Now this isn't a formula that I have my students memorize, we just want to be able to use it, to be able to look it up and use it when we have it. So if A is 5x, B is 3x, A plus B is 8x, A minus B is 2x, and now I've succeeded in writing what was a product as a sum. And as I said, in some fields, some math classes you're going to take later on in engineering classes and that, it's important to be able to write a product of 2 trig functions as a sum. Let's look at one more problem. I want to simplify cosine 45 plus cosine 15. Now, what we want to see is that this looks like cosine A plus cosine B. Now, in the book, cosine A plus cosine B, a formula that takes us from a sum back to a product, is this formula. Cosine A plus cosine B is equal to 2 cosine A plus B over 2 times cosine A minus B over 2. And again, this formula right here is derived in the book. You're going to have to look it up in the book to see exactly where this came from. But the purpose of this formula is if you have a sum of 2 trig functions, you can write it as a product. Okay, so let's see if we can apply it to this problem right here. So A is equal to 45 degrees, B is equal to 15 degrees. That means that cosine 45 plus cosine 15 is going to be 2 cosine of 45 degrees plus 15 degrees over 2 cosine of 45 degrees minus 15 degrees over 2. And that's 2 cosine of 45 plus 15 is 60, divided by 2 is 30. Cosine of 45 minus 15 is 30, divided by 2 is 15 degrees. And I suppose, since I know cosine of 30 degrees is square root 3 over 2, I could write this as 2 times square root 3 over 2 if I'm working with exact values. Cosine of 15 degrees, those 2's divide out, and I get square root 3 cosine 15 degrees. Okay, now, again, you're going to have to wait and see where these problems are going to come up later on in other math classes or in your science or engineering classes. But there are times when you have an expression that has the sum of two trigonometric functions. You want to rewrite it back as a product. Just like in the previous problem, we had a product of the sum of the product of two trig functions. We wanted to rewrite that as a sum. So these last identities, like this one right here, again, they're not the kind of identities I have my students memorize, but I do want them to be able to work with them. So you have an expression like this, you have to look through the list and see what expression it is similar to, and then rewrite it using the formula that you're given. So that's a look at some additional identities for trigonometry.